Integration of even and odd functions over symmetric intervals. Okay, so we've been working with definite integrals, and now we're going to learn a really neat trick that can save us a lot of time. This slide introduces a special property. We call it property P subscript 7. This property is all about making the calculation of definite integrals much faster when we're dealing with what are called symmetric intervals. Remember, a definite integral, at its core, represents the area under a curve. And sometimes, the symmetry of the function or the interval we're integrating over can dramatically simplify finding that area. Specifically, this property lets us evaluate integrals over an interval of the form minus a to a, that is, an interval that extends equally in both positive and negative directions from 0, almost instantly. But here's the key. It only works if we can determine whether the function we're integrating, what we call the integrand, is either an even function or an odd function. We'll be diving into what even and odd functions are in the next few slides, but for now, just think of it as identifying a certain parity of the function. If we can quickly tell if a function is even or odd, we can use this property to avoid a lot of complicated calculations. So, understanding even and odd functions is crucial for applying this property effectively. We'll build on this concept in the following slides, so pay close attention. Understanding symmetric intervals. Firstly, a symmetric interval simply extends equally in both directions, the positive and negative directions, starting from 0 on the x-axis. Think of it like a mirror image around 0. Now, mathematically, we represent this symmetric interval as minus a to a, or written as a $. Here, a represents any positive real number. So, a could be 5 or pi or 1 as long as it's a positive number. It defines the boundaries of our symmetric interval. Let's look at some examples to make this crystal clear. We have negative 5 to 5, which is minus $5. Then we have negative pi to pi, written as \pi $. And finally, negative 1 to 1 or minus $1. Notice how in each case, the interval is balanced around 0. The distance from 0 to the negative endpoint is the same as the distance from 0 to the positive endpoint. Okay, so let's move on to slide 2. As we discussed on the previous slide, we're learning about a shortcut for integrating functions, specifically when the function is either even or odd. But this shortcut only works under a specific condition regarding the interval we're integrating over. That condition involves what we call a symmetric interval, and that's what we're going to define right now. Why is this important? Well, as we'll see in the following slides, this symmetry is key to simplifying our integration process when dealing with even and odd functions. If the interval isn't symmetric, we can't use these handy properties. So, always double-check your limits of integration before applying the shortcuts we're about to learn. Even functions. Now, looking at the slide, we have the definition of an even function. It states that a function, which we denote as f of x, is considered even if, for every x value within its domain, the following condition is true. F of negative x is equal to f of x. Let me say that again. F of negative x equals f of x. What this essentially means is that if you plug in a negative value for x, you get the same output as when you plug in the positive version of that value. Now, let's look at the geometric interpretation. An even function has a very specific visual characteristic. It's symmetric with respect to the y-axis. Imagine folding the graph along the y-axis. The left side would perfectly overlap with the right side, like a mirror image. This symmetry is the hallmark of an even function. This symmetry leads us directly to the integration property. Because of the symmetry, the area under the curve from negative a to 0 is exactly the same as the area under the curve from 0 to a. Think about it visually, they're mirror images. Therefore, when we integrate an even function over a symmetric interval from negative a to a, we don't need to calculate both integrals separately. We can simply take double the integral from 0 to a mathematically. This is represented as the integral from negative a to a of f of x dx is equal to 2 times the integral from 0 to a of f of x dx. To help solidify this, let's consider a real-world analogy. Imagine a perfectly symmetrical bridge arch. If you were to calculate the area enclosed by the right half of the arch, you could simply multiply that area by 2 to find the total area under the entire arch. This is because the left half is a mirror image of the right half, just like with even functions. Okay, let's move on to our next important concept, even functions. As we discussed on the previous slides, understanding these function types is key to simplifying integrals over symmetric intervals. Keep this in mind, as we'll be applying this property in the examples coming up on the next slides. We'll see how this can significantly reduce the amount of calculation needed to evaluate certain definite integrals. Odd functions. Okay, so let's move on to the next type of function, odd functions. As we discussed on the previous slides, identifying whether a function is even or odd is key to simplifying integrals over symmetric intervals. Now, looking at the slide, the definition of an odd function is as follows. A function, which we denote as f of x, is considered odd if, for every x value within its domain, the following condition is true. F of negative x is equal to negative f of x. Let me say that again. F of negative x equals negative f of x. This is the crucial test to determine if a function is odd. Let's think about what this means geometrically. Odd functions have rotational symmetry about the origin. Imagine taking the graph of an odd function and rotating it 180 degrees. That's a half turn around the point 0, 0, which is the origin. The graph will look exactly the same after the rotation. It's like it's been spun around. Now, how does this symmetry help us with integration? Well, for an odd function, the area under the curve on the interval from negative to 0 is exactly the negative of the area under the curve on the interval from 0 to a. Think of it as one area being above the x-axis and the other being below. Because of this equal and opposite area, when we sum these two areas together over the symmetric interval from negative to a, they completely cancel each other out. This leads us to a very powerful integration property. The definite integral of an odd function from negative to a is equal to 0. We can write this as integral from negative to a of f of x dx equals 0. To help visualize this, let's consider a real-world analogy, a balanced seesaw. If the weight, and in our case, the weight represents the area under the curve, on the left side of the seesaw is exactly equal and opposite to the weight on the right side, relative to the center, the net result, or the integral, is 0. The seesaw is balanced, and the integral is 0. Keep this in mind, as we'll be applying this property in the examples on the next slides. And remember, just like with even functions, correctly identifying whether a function is odd is the first step to using this shortcut for integration. Step-by-step examples. Okay, let's work through a couple of examples to solidify our understanding of integrating even and odd functions. This is where things really start to become efficient, remember. We've established the properties, and now we're going to use them. This first example focuses on an even function. We're asked to evaluate the definite integral of x to the power of 4 plus 3 from negative 2 to positive 2. Let's write that out. The integral from negative 2 to 2 of x to the power of 4 plus 3 with respect to x. Step 1, check the interval. This is crucial. We need to make sure we can actually apply the shortcut properties we discussed. The interval is indeed negative 2 to 2, which, as we know from our earlier discussion, is symmetric about the origin. That means it extends equally in both the positive and negative directions. Good, we're on the right track. Step 2, determine the parity of the function. Now we need to figure out if the function inside the integral, x to the power of 4 plus 3, is even or odd. Let's define f of x as x to the power of 4 plus 3. To check for evenness or oddness, we substitute negative x for x, so f of negative x becomes negative x to the power of 4 plus 3. Remember, negative x to the power of 4 is just x to the power of 4, because a negative number raised to an even power becomes positive. Therefore, f of negative x simplifies to x to the power of 4 plus 3. Notice something important. This is exactly the same as our original f of x, since f of negative x equals f x. This confirms that our function is even. Excellent. Step 3. Apply the property. Now the magic happens. Because we've identified the function as even and we have a symmetric interval, we can use the property we learned earlier. The integral from negative to a of an even function f of x is equal to 2 times the integral from 0 to a of f of x in our case. Is 2. So, the integral from negative 2 to 2 of x to the power of 4 plus 3 dx is equal to 2 times the integral from 0 to 2 of x to the power of 4 plus 3 dx. See how much simpler that is. We've effectively halved the interval we need to integrate over. Step 4. Solve the simplified integral. Now we just need to evaluate the simpler integral. 2 times the integral from 0 to 2 of x to the power of 4 plus 3 dx. First, let's find the indefinite integral of x to the power of 4 plus 3. The indefinite integral of x to the power of 4 is x to the power of 5 divided by 5, and the indefinite integral of 3 is 3 times x. So we have x to the power of 5 divided by 5 plus 3x now. We evaluate this from 0 to 2. That means we plug in 2 and then subtract what we get when we plug in 0. Plugging in 2, we get 2 to the power of 5 divided by 5 plus 3 times 2. 2 to the power of 5 is 32, so that's 32 fifths plus 6. Plugging in 0, we get 0. So we have 32 fifths plus 6. Let's combine those terms. 6 can be written as 30 fifths. So we have 32 fifths plus 30 fifths, which equals 62 fifths. But remember, we have to multiply this by the 2 that was outside the integral. 2 times 62 fifths is 124 fifths. And there you have it. The integral from negative 2 to 2 of x to the power of 4 plus 3 is equal to 124 fifths. We successfully used the property for even functions to significantly simplify the calculation. In the next example, we'll do the same with an odd function. Step-by-step examples continued. Okay, let's move on to our second example. This one focuses on integrating an odd function over a symmetric interval. Slide 6, Example 2, Evaluating an odd function. Here, we want to evaluate the definite integral of sine of x from negative pi to pi. That's written as integral from negative pi to pi of sine of x dx. Step 1, check the interval. As always, the very first thing we do is verify that our interval is symmetric. And as you can see, the interval is negative pi to pi. This is a symmetric interval because it extends equally in both positive and negative directions from the origin. Remember, a symmetric interval has the form negative a to a, and in this case, a is pi. Step 2, determine the parity of the function. Next, we need to determine if the function, sine of x, is even, odd, or neither. Let's define our function as f of x equals sine of x to check for odd or even functions. We substitute negative x in place of x, so f of negative x is equal to sine of negative x. Now recall a key trigonometric identity. Sine of negative x is equal to negative sine of x, therefore, we have f of negative x equals negative sine of x, which is the same as negative f of x, remember the definition. If f of negative x equals negative f of x, then the function is odd. So, sine of x is an odd function. Step 3, apply the property. Now that we've confirmed that sine of x is odd and our interval is symmetric, we can apply the property we discussed earlier. For an odd function integrated over a symmetric interval from negative a to a, the result is always 0. Therefore, the integral from negative pi to pi of sine of x dx is equal to 0. And that's it. We've evaluated the integral simply by recognizing the function's parity and the symmetry of the interval. This saved us from having to actually calculate the integral, which can sometimes be quite complex. In the next slide, we'll discuss some common mistakes students make when applying these properties, so pay close attention to those to avoid falling into those traps. Common mistakes to avoid. First, let's talk about ignoring the interval. A very frequent error is trying to use these properties, the shortcut of multiplying by 2 for even functions or getting 0 for odd functions, on intervals that aren't symmetric. Remember, a symmetric interval looks like this: negative a to positive a, where a is any positive real number. For example, -5 to 5, -pi to pi, or -1 to 1. If you have an interval like 0 to 2, or -1 to 3, these properties simply do not apply. They only work when the interval is perfectly balanced around 0. Next, we have incorrect parity identification. This is about correctly determining whether a function is even or odd. Sometimes, you're not dealing with a simple function like x to the power of 4 or sine of x. You might have a combination of functions multiplied together. It's crucial to remember these rules. An even function multiplied by an even function results in an even function. An odd function multiplied by an odd function also results in an even function. And an even function multiplied by an odd function gives you an odd function. Let's look at an example. Consider the function x squared times sine of x squared is an even function, and sine of x is an odd function. Therefore, their product, x squared sine of x, is an odd function. Finally, let's address sign errors. This one is particularly tricky when dealing with odd functions. When you're checking if a function is odd, you need to make sure that substituting -x into the function results in the negative of the original function. Don't just look for any change. It has to be a complete sign reversal. Let's illustrate this with an example. Consider the function f of x equals x cubed plus 1. If we substitute -x for x, we get f of -x equals -x cubed plus 1. Now, compare this to the original function, f of x. Notice that -x cubed plus 1 is not the same as x cubed plus 1, and it's also not the negative of x cubed plus 1. Therefore, this function is neither even nor odd. It's important to check the entire function to confirm the sign change. Okay, let's move on to slide 7. This slide is really important because it highlights some common pitfalls students make when applying the integration properties we've just learned for even and odd functions. We want to make sure you avoid these mistakes so you can confidently tackle any integration problem. So, keep these common mistakes in mind as you practice. By being careful with the interval, correctly identifying parity, and avoiding sign errors, you'll be well on your way to mastering this powerful integration technique. Now, let's move on to the final slide where we'll summarize everything we've learned. Key takeaways. Okay, let's recap everything we've learned about integrating even and odd functions. This slide serves as a neat summary, a quick reference guide if you will, to help you solidify these concepts. We have a table here with 4 columns: function type, condition, symmetry, and integral over a. Remember, we've been focusing on integrals over symmetric intervals of the form a, where a is a positive real number. Let's start with the first row, dealing with even functions. As we discussed earlier, a function is considered even if, for every value of x, f of -x is equal to f of x. In other words, if you substitute -x into the function, you get the same result as substituting positive x geometrically. This means the function is symmetrical with respect to the y-axis. And crucially, the definite integral of an even function from negative a to a is equal to 2 times the definite integral from 0 to a. So, we can calculate the integral over the entire symmetric interval by simply doubling the integral over the positive half. Now, let's move down to odd functions. A function is odd if, for every value of x, f of -x is equal to -f of x. This means that the function exhibits rotational symmetry about the origin. A 180-degree rotation around the origin leaves the graph unchanged. And the big takeaway here is that the definite integral of an odd function from negative a to a is always 0. This is because the area under the curve from negative a to 0 perfectly cancels out the area from 0 to a. So, this table provides a concise way to remember the key properties. If you can quickly identify whether a function is even or odd, and you're integrating over a symmetric interval, you can significantly simplify your calculations. Keep this slide handy as a quick reference as you practice more problems. In the next set of problems, we will be applying these concepts to more complex functions, so make sure you have a firm grasp of these fundamentals.